Hello, welcome back to probability modeling. Today, as you can see, we're going to cover chapter 5. This is another quite short chapter, so I expect we can finish it or almost finish it today. Let's see what happens. Alright, so you can see the title of this chapter is Hitting Times and Probabilities, specifically hitting times and probabilities of Markov chains. So let's quickly explain what the idea behind this chapter is. It's quite simple. So we have a Markov chain and we have one special state or a group of special states for which we're interested in two questions. First is it possible for the chain to ever hit this, and what's the probability of this happening? So probability of hitting a certain state or a certain family of states. And second, how long is the expected time until we end up hitting this set? And so in this chapter, we will basically see how to answer these questions, how to find this hitting probabilities and expected hitting time. And we'll go through a few examples. There's not really much theory and definitely no theorem you should learn. What you need to do is understand the method of how to do this and how to get your results. So it's actually quite simple. So let's start with these hitting probabilities, which can also be called absorption probabilities sometimes. So take a Markov chain on a finite state space. And as we've seen before, there's always at least one closed class. And if there is exactly one, then we will eventually end up inside this closed class and of course never leave it. So this is not what we're interested in, because in this case, like probability of entering the closed class is 1. That's great. What we're interested in is if there's more than one, if there's at least 2 closed classes, then something interesting happens. If we start at a transient state, then we may end up in one closed class or in another. And that's random. And so we're interested in the probability of one or the other happening. So if you take a closed class C, then we're going to call QIC the probability that we end up inside C if we start at state I. And a quick reminder of notation, this is actually equals to Fij for J a member of C, because as we've seen before, if you enter C, then you will visit J eventually at some point. And F is the probability of, Fij is the probability of visiting J at least once if we start from I. So we're interested in these QICs, probability of entering C starting from I. And since we can't exit C, we call this an absorption probability. So for completeness, QIC was defined first for a transient state, but it can be defined for any state. So if I is inside of C, then QIC is 1 because we're already inside. While if I is in a closed class which is not the closed class C which we're interested in, then it's 0 because we're never going to enter C. And as you will see in the examples, the C is always fixed, like we choose a C, and so we don't actually need to mention it. So usually QIC will be just called as QI. And it's also good to know that if the closed class has only a single state, then we call it an absorbing state. And this is really absorbing in most literal sense you can think of, because it means if you hit that state, you're never going to move anymore. So you die there, basically. Okay, so how do I find QIC? Well, the general strategy is what's shown here, and it's pretty simple. So you just use the Markov property after one step of your Markov chain. So to do that, call DC the event where we end up in C. So it's the event of which we want to know the probability. QIC is the probability of DC when we start at point I. And if we take one step of the Markov chain, what happens? Well, we end up at a certain J, and then for DC to happen starting from I, it's the same thing as first going to J, and then DC happening starting from J after one step. So we end up with the sum over all possible J's of probability of going to J and then having DC. So this is actually the law of total probability. And then by the Markov property, this is just QJC. It's just probability of entering C starting from J. And by definition, of course, this is Pij. So we get that QIC is the sum of Pij QJC for any other J. So this is interesting for I, a transient state, of course, because if I is not a transient state, then we already know that this is 1 if I is in C, and this is 0 if I is not in C. So we get these linear equations. And to emphasize what I said before, if I is in one of the closed classes, then this equation gives us nothing. So as I said, we know this is 1 or 0, but this will also be 1 or 0. So why is that? If I is in C, then all the J's which matter, sorry, I'm going to go back and forth. All the J's which matter here will also be in C. So these will all be 1, so this will end up being 1. And if I is outside of C, this is 0. And for all the J's which matter, this is also 0. Both sides are either 1 or either 0 if I is in any closed class. So in any case, we have these linear equations, which, if you're interested in algebra, mean that the column vector with the QICs is an eigenvector of the transition matrix on the right, and the eigenvalue is 1. And each equation really is just a row of the transition matrix. So because the Markov chain is not irreducible, or more specifically because it has two closed classes, we know that there's the dimension of the space of these eigenvectors is more than one-dimensional. And so your answer, the solution to this does not need to be 1, 1, 1, 1, 1, 1, 1. It will be an actual interesting vector. And yeah, this is just how you do it. So we get these equations. So as we said, we get 1 for each transient I, and then we can just solve them. And of course, we got the other equations that QIC is 1 if I is inside C and 0 if I is outside of C, which we also need to use in order to solve the whole system. And we call those the boundary conditions, because that's quite a typical thing to do. And you will need to do that to use this to solve the system. Okay, so this is enough abstract presentation. Let's go over this with an example. So let's write a little bit. Let us take an example, which I'm going to call example 28. It's a simple Markov chain model of a university course. University course model. So I have a student who's at university for a 3-year course, and each year the student can do 3 things. He can either pass his year, or he can repeat his year, or he can just quit university altogether. Too bad for him. So, and with a very convenient notation, he passes with probability P. He repeats his year with probability R, and he quits with probability Q. We got PQR, 3 consecutive letters. And so what's my question? What is the probability that a student graduates? So of course, students may quit before graduating, and we're interested in the probability of this not happening. Well, so of course this model is not realistic, but we can play with it, and in particular we get a Markov chain with 5 states. So the 5 states are year 1, year 2, year 3, and graduated and quit. And the transition matrix, if you think about it, it's actually quite natural. So we said if I'm on my first year, I will repeat my first year with probability R. So with R, I'm going to stay at the first state. I'm going to pass to second year with probability P. And of course, if you're first year, you can't jump to third year, so nope. And you also can't graduate yet. So here's another 0, and you quit with probability Q. Of course, R plus P plus Q equals 1, because otherwise this would be incomplete information. If I'm on my second year, well, you can't go back. You can repeat probability R, you can pass to third year, you can't graduate yet, you can still quit. If you're on your third year, well, you may repeat, you may pass, in which case you graduate, congratulations, or you may quit, so close, but no. Meanwhile, these other states, if you graduated, then we're not going to move, and if you quit, you're not coming back. So these rows, these 2 final rows mean that the graduated and quit states are absorbing. So states 4 and 5 are absorbing. And the question is, find the probability of graduating. So let Qi equals probability of being absorbed at 4. For I being 1, 2, 3, or 4. And so we do the thing we said. So first there's the boundary conditions. Q4 equals 1. So if I start graduated, I stay graduated because I'm already absorbed. Q5 equals 0. So I start in the wrong absorbing state. And what's more interesting is the other ones. So Q1, we do this linear equation thing. Start in year 1 and take 1 step of the random walk. So with probability R, you don't move. So there's R Q1. With probability P, you move on to the next year. So P Q2. And you can also quit Q Q5. And of course, this is 0. Then we have Q2. Same thing. You may repeat RQ2. You may pass P Q3. You may quit Q Q5. And again, this is 0. And finally, last equation, Q3 is RQ3 plus PQ4 plus QQ5. This is 0 again, and Q4 is 1. So really this is just P. And now we can solve this. We can kind of go backwards because we have Q3 is going to be explicit, of course. So solve backwards. Q3. So Q3, you got RQ3, so put this on the left side. Q3 times 1 minus R is P. So Q3 is P divided by 1 minus R. And then Q2 equals, so Q2, again, Q2 times 1 minus R is P times Q3. And so we get Q2 is P squared divided by 1 minus R squared. And same thing, Q1 is P cubed divided by 1 minus R cubed. And that's it. This is really what we're interested in. This is the probability that a student who just entered ends up graduating. We wish the student the best luck. You know, hopefully P is high and R is small. All right, so I hope this was clear. And now let's do another example in example 29. Which is a gambler's ruin, something we've seen before. So let's say probability of ruin. So remember, so we have a gambler's ruin model. So we need a bit of notation. P is probability of success at a step. Probability of success. Q is probability of a failure. And N is our target. So remember, you flip a biased coin, which is heads with probability P and tails with probability Q. If it's heads, you win 1 money. If it's tails, you lose 1 money. And you stop if you have 0 money or N money. So 0, you've been ruined, and N, you reach your target. You win in some sense. And so we're interested, let's say, let Qi equals probability of hitting N starting from I. Probability of hitting N starting from I. So probability that my absorption is at the success event, so at the target amount of money. Then Qn equals 1, Q0 equals 0. So again, that's the boundary conditions. And our linear equations, if I take I, which is in the middle, Qi is, well, take one step. Either I win the one step, in which case I reach I plus 1, so it's probability of reaching N starting from I plus 1, or I lose, probability Q, and then I want Qi minus 1. And can we solve this? Well, actually we can. It's a bit harder than what we've had before, because this is a linear recurrence equation, but with 3 things. three terms appearing at the same time, so it's a degree 2 equation, maybe a little bit difficult. Well, I think you've learned how to do this, but in this case there's a simple trick which makes this one easy to solve. So you notice that p plus q equals 1, so we can write p plus q times qi is p times qi plus 1 plus q times qi minus 1. And let's move on to the next page. And we can rewrite this. To compare the two pages, you can rewrite this as q times pi minus 1 equals p times, these are q's, sorry. Always was qi. Q times qi minus 1 is equal to p times qi plus 1 minus qi. And this is interesting. We see that there's some kind of geometric sequence which comes out. If we let's say di equals qi plus 1 minus qi, then we have di plus 1, let's put it like that, is equal to q divided by p di. Alright, because that was di plus 1, so just bring this p here. And so this di is just a geometric sequence. So we get di is q over p to the power n to the power I times d0. Q over p to the power I times d0. Now, well, we've almost solved things. Now we just need to mess around with a little bit more information we have. So di, I know di, this lets me get qi back. How do I do that? We can get qi back because qi is equal to d0 plus d1 plus ... plus di minus 1. So if you know how geometric sums work, you know that we get d0 times, so this is the sum for k equals 0 to I minus 1 of q over p to the power k. And so this is nothing else but d0 times 1 minus q over p to the power I divided by 1 minus q over p. So a little bit of an annoying fraction, but we have our qi, except that d0 is still unknown. We need to find d0. So that's the thing left to do. Now find, well, actually I cheated a little bit here, right? So I said the sum of this geometric sum is this thing because of a formula we know. This works if q different from p. Because if q is equal to p, then we divide by 0 here and it's not going to work out. So let's concentrate on this for now, and we'll see what happens if q equals p later. So if q is different from p, so we get this, and I said let's find d0. Well, we can use the boundary conditions to find d0. We know in particular that qn, capital N, is equal to 1. And that's all we need, really. Qn is equal to 1 is equal to d0, 1 minus q over p to the power n divided by 1 minus q over p. So d0 is the inverse of that. So d0 is 1 minus q over p divided by 1 minus q over p to the power n. And so we get our conclusion. Qi is, so just put the d0 back inside, and we get Qi is equal to 1 minus q over I to the power, q over p, sorry, to the power I, divided by 1 minus q over p to the power capital N. And this is the answer. Well, this is the answer when q is different from p. If q equals p, in which case they would both be 1/2, then we can't use this geometric sum here. Instead, this is the sum of 1. So we get Qi equals d0 times the sum of things which are all equal to 1. There's I terms. So we will get Qi equals I times Q0 times d0. So I'll let you finish that, but we get Qi equals I times Q1, and so it has to be I over N. So same thing, but easier. Okay, so these are 2 examples, and this is how you do the thing. So to find out where you get absorbed, you just write your 2 linear equations, and your linear equations here, it's Qi expressed in terms of Qi plus 1 and Qi minus 1, and then you solve things as you know that you can solve them. Okay, let's go back to the slides. And let's look at something slightly different, but actually not really different. So now suppose that I have an irreducible chain. So there's only one closed class, and everyone is a closed class. And so there's no absorption to speak of, but we can still create something interesting and just say, well, I take 2 sets, C1 and C2. And I'm interested in the probability of reaching C1 before C2 or reaching C2 before C1. And we can actually treat this exactly as what we did. And now we set these Q's again. So Qi C1 is the probability of hitting C1 before C2. And this thing is 1 if I'm in C1, and it's 0 if I'm in C2. And then you can use the same method of obtaining linear equations. Except that we're going to naturally ignore all equations which come from rows of the matrix, which corresponds to states in C1 or C2. So if this sounds abstract, we'll do an example in 2 minutes, and this is really, the example is the way to see it. But if you're interested in the theory, basically what we're saying is that we're modifying the chain to make C1 and C2 absorbing. And when I've made them absorbing, I can apply things I've done before. Why can I do that? Because when I've hit them, it doesn't matter what the transition probabilities are. I can change what happens once I am inside, because I only care about when I reach the inside. And so, let's do an example. Random walk on a cube. So, example 30. So I've got this cube. Let's draw a cube the best we can. So on one side I've got A, B, C, D, and then I have the back side which is E, E, F, G, H, like that. This is my cube. And so we do a random walk on a cube. So if I'm at A, I choose one of my neighbors, B, D, or E, with probability 1/3 for each. And the question is, what is the probability of hitting the backside, E, F, G, H? So probability of hitting any of those before C. Before C, starting from A. So we're gonna let Q I, so for I being one of the 8 letters, equals probability of hitting E, F, G, H before C, starting from I. So we want these probabilities for every point. So even though we're only interested in QA, we need to define all of them. And so we have, it's like before, boundary conditions. QC is 0, because we're already in the wrong place. Meanwhile, QE equals QF equals QG equals QH equals 1, because we're already where we want. And then the other states will give us equations. QA is, we said, 1/3 of QB plus QD plus QE. And this one is 1. Okay, because with probability 1/3, I end up in either of those. QB is 1/3 of, well, there's going to be QA, and there's also C and F. QC, that's 0, and QF, that's 1. And finally, QC, not QC, QD, that's the only one we haven't touched yet. QD is 1/3 of QA plus, so D is connected to C, so there's a 0, and there's QH, that's 1. Okay, so if you look at our 3 equations, you see that, so QA is expressed in terms of QB and QD, and QB and QD are also expressed in terms of QA. So replace this QB by 1/3 of QA plus 1, and replace this by the same thing. We get an equation for QA. I'm not gonna go through the details. You can do that yourself if you feel like it. But we end up with QA equals 5/7. I mean, there's not much details. Skipping at most 2 or 3 lines. But yeah. So this is how you do it. And you can see that there's virtually no difference between this example and the previous ones. I just set my Q's being the probability of what I'm interested in. Then I got those boundary conditions. And then I got the equations for the states which are not in either E, F, G, H, or C. Okay, so that's all for hitting probabilities. So I've shown you how you can compute the probability of hitting a certain state before another state, or being absorbed at this place or that place. Now I'm interested in something different, which is the expected time to absorption. So take a Markov chain which has at least one closed class. So if you start at a transient state, you will eventually be absorbed into a closed class. Let's just say, for example, that the state space is finite, because this is typically what happens to us. And so the number of steps until absorption is a random variable, and we're interested in its expectation. Specifically, we call it TI, and then EI is its expectation. So EI is the expected time until absorption starting at state I. And like we've seen before, if I start in the closed class I'm interested in, well, in a closed class this time, then expected value of Ti is 0. So, and Ti itself is also 0, of course. And the question is, how do I compute these EIs? It's going to be very similar, actually. So we want, again, linear equation solved by the EIs. And again, we're going to take one step, condition on this first step, and then use the Markov property with the expectation this time. And basically what happens is that if I start at I, and I go to state j, then this took me 1 unit of time, 1 step, and so I take 1, and then it's going to take, on average, tj to reach absorption. And this is the more slightly formal version. So EI is the expected value of Ti, and we condition on the first step. So I go to a certain j, and what is Ti knowing that I went to j? Well, in this case, Ti is going to be 1 plus Tj, because when we start at j, then the time until absorption has the distribution Tj. So this expectation here is actually just 1 plus expectation of Tj. So this thing now is Ej, and we got a sum of Pij, so this is 1. We can put this out of the sum, and then sum of Pij, Ej. Again, this may look a bit abstract. We're just saying, so what's the average time to absorption starting from I? Well, you need to take one step. That's that 1, because you need to take a step, first step. And then we reach a certain j of probability Pj, and now we got to get absorbed starting from j. So the time on average is Ej. Okay, and if this is not very convincing, we're going to go to an example very soon. But first, so we have this system of equations. You can actually restrict the j's to those who are transient, because otherwise Ej is 0. We've talked about that. And we have a collection of linear equations. We know there's no problem. This has a unique solution, so you can just work on solving it. So let's go through an example, as I said. So we're going to go back to the university course model. And we're going to ask, example 31. How long, on average, well, what's the expected time that a student stays inside university? So remember, we have this model where we have P, probability of passing to the next year, Q, probability of quitting at any year, and R, probability of repeating a year. So let's maybe, I'll just write university course model here. As a recap. So, this model had 5 states, 1, 2, 3 being year 1, year 2, year 3, 4 being graduated, and 5 being having quit. So of course, E4 equals E5 equals 0. So we're saying that, no, in theoretical terms, if you're already absorbed, then the expected time until absorption is 0. In practical understanding, if you've graduated or if you've quit, you're not at university anymore, so the expected time you're going to stay there is 0. Meanwhile, the other ones will give us interesting linear equations. So E1. So you're a first year student. You're going to spend your first year, whatever happens. So there's a 1 plus, well, either you're repeating, so R E1, or you're passing, P E2, or you're quitting, Q E5, and as we've said, E5 is 0. If you're a second year student, well, you're going to spend your second year, so there's a 1, plus you may repeat it, in which case it's going to be E2 again, or you may pass, in which case you're going to have E3, or you may give up, which is again 0. And finally, E3 is, well, you got to spend your third year. Maybe you'll repeat it. Unfortunate. Maybe you'll pass and you'll finally graduate. If you do that, you're done. So E4 is 0. And again, you may quit. This is also nothing. And now, as before, we can solve this backwards. So we get E3, though it's simpler than before. E3 just passes to the left. We get 1 minus R and you divide. E3 is equal to 1 divided by 1 minus R. E2. So E2, so you get 1 minus R E2 and you get 1 plus P E3. So you're going to get 1 over 1 minus R plus P divided by 1 minus R squared. Okay, so this comes from the PE2 divided by 1 minus R, which came from that, and this comes from this 1 divided by 1 minus 1 minus R. And finally, E1, the one we're really interested in. So you get, again, put this on the left side, you get 1 over 1 minus R plus PE2 divided by 1 minus R. So we get P divided by 1 minus R squared plus P squared divided by 1 minus R cubed. And that's the answer we were looking for. This is the expected amount of time a student stays at university. And of course, this makes sense. If P is very close to 1, then this is going to be very close to 3. So things make sense. And that is also good. Okay, so this is how you can compute an expected time until absorption. You could do this for the cube as well if you wanted to. That would be not a bad exercise at all. And we're almost done with today. Let's go back to the slides. As before, you're going to have a variant of this where you don't need to assume that there exists an absorbing state or an absorbing class. Instead, you can look at the expected time until the chain arrives at a certain state or a certain group of states, which doesn't have to be absorbing. And you do the same method, which is, for example, if you're interested in the expected time until we reach J, then you're going to set EJ equals 0, because if you're at J, there is no time until you reach that. And then write the linear equations for all the other states and discard any equation coming from J, because that wouldn't be useful. And that's the same thing as, like before, make J absorbing by removing any transition outside of J. That would be equivalent. Again, we'll just go with an example, and that will be the end of this video. And we're going to look at something we've seen before, which is patterns in coin tossing. So specifically, example 32. Find the expected number of throws so you throw a coin repeatedly and you're interested until that's an L, until we reach the state, let's say THT. So keep throwing your coin and stop when you have tails, heads, tails in a row. So this is something we've solved before with renewal processes. But we can actually do this with this Markov chain expected time method. So how do we do this? So first off, we need a good Markov chain. So this is where you may need a bit of imagination, but define a Markov chain. I'm going to write MC for Markov chain, where the states are what we're going to call partial achievement. Partial achievement. Okay, that's a bit hard to read. I'm sorry, but I hope you're listening. Partial achievement of this THT. So basically, this Markov chain means that you got to build the THT progressively. So if you throw a tails, then you're making progress. But if you throw a second tails after the first one, then you're not making progress. Similarly, if you have TH, but then you throw H, then you've ruined everything and you're going back to a starting point. And this is the idea behind this Markov chain. So we have 4 states. 0 is not currently building a THT. So for example, that's right at the beginning, we're at state 0, or if you've thrown 2 H's in a row, then you're at state 0. State 1 is have the first T. State 2 is have TH. And state 3 is you're done, you have THT. Congratulations. So this is a Markov chain, and the best way to see how it's a Markov chain is really to write down its transition matrix. So transition matrix, we call it P as ever. So let's say we start from nothing or from 2 H's in a row. Then if I throw an H, then I still have not done any progress towards building a THT. So there's a 1 here. But if I throw a T, then I have my first T. So I've reached state 1. If I have a T, so I can throw a T or an H, which means I will either have TT or TH. So if I have TT, actually it's the same as just not moving, because TT is just a T. So having the pair TT is not advancing me towards THT. I'm just starting again THT from the second T. But if I throw in an H, then I have TH. Then I'm closer to success. This matrix needs to go lower down. If I have TH, if I throw H again, that's unfortunate. I go back to nothing, because I'm going to have to toss a first T again. And on the other hand, if I throw a T, then I have my THT and I win. Meanwhile, if I'm at THT, so what happens? If I'm at THT, it's kind of like restarting again. And this line doesn't really matter, because it's going to be our absorbing state, well, our fake absorbing state. But we have a T, So it's basically this again, the same as this line. But as we will see, this line doesn't matter. And so, what are our expected times? So E3 is 0. That's because I've succeeded. E2, let's go backwards, is 1, because you got to do your toss, plus a half of E0. So that's if I landed back into state 0, plus a half of E3. And of course, that's nothing. E1 is 1 plus, so if I'm at state 1, I may move to state 2 or stay at state 1. So half of E1 plus half of E2. And E0 is, well, as you see here, 1 plus half of E0 plus half of E1. And now I can solve this. So again, it's a bit of a mess, but I have E1 in terms of E0, and I got E2 in terms of E0, so you could plug this in back here, you would get E2, and plug this in, plug this in. Okay, that was a bit unclear, but you know how to solve this. I'm not going to do it, and we end up with E0 equals 10. And that should be the same answer we found when this was done with renewal processes. And there we are. We are done. This is actually the end of this chapter. So the moral of the story is, if you're interested in the probability of hitting a certain group of states before another, or the expected time before hitting a certain group of states, take one step of the Markov chain. This lets you write linear equations and write your boundary conditions, which are what happens if you're already inside the target places. And your linear equations will have a 1 plus if you're looking at expected times, because it takes 1 unit of time to take a step. They won't have the 1 plus if you're just looking at probabilities. And then solve your linear system, which I was a bit too lazy to do here, and you get your final answer. So you're now equipped, I believe, to do all the exercises corresponding to chapter 5. So you're welcome to try and do them. If you have questions, you should come to the virtual office hour, which I'm going to set up right now. So give me a second and I will paste a link. To Google Meets. Start a meeting. And I will need to fix my webcam because it's currently used by the stream, of course. And here is the link. I'm going to paste this in the YouTube chat and also paste it in the video description. And that should be done. So that was today's lecture. Next Tuesday we will start on chapter 6, the last chapter of the course. All right. See you then. Bye. Have a good weekend.